We're going to talk about proofs today. Before we do that, though, I would like to ask you a question. If I said, write down an equation I'm going to give you a sentence, and I want you to write that down as an equation. Here's the sentence. The sum of two numbers is 4. How would you write that down as an equation? The sum of two numbers is 4.
X plus y equals 4.
Exactly what I have written down on my piece of paper right here. That's exactly what I wrote. X plus y equals 4. Now, notice you didn't write x plus x equals 4, right? Because you think, oh, a number, well, x. And you didn't go x plus x equals 4. Now, we'll get back to that in just a second. So if then I give you some information and I said like one of those numbers is 2. And you say, well, okay, if one of those numbers is 2, maybe I'll think about that as like x equals 2, okay? And so then you plug it in and you say, well, one of those is 2. So what you're saying is 2 plus a number is equal to 4. Then what would you do to find the other number? Or just what is the other number?
2.
The other number has to be 2, right? Because you could say, okay, well, minus 2 from both sides. And you get that y equals 2. In this special case, once I gave you the second bit of information right here, right? Then it happened to be the case that x was equal to y and that they were both equal to 2. It happened to be that case. But in general, when the very first thing that I gave you, just the only information I gave you, you assumed, and you assumed rightly, that, well, let's give them different names. Because yes, even though it might be the case that they're both equal to the same thing, in which case we could have written x plus x equals 4. That's a special case. And at the very beginning, we didn't know that that was going to work out that way, right? Okay.
Right.
And so the idea here is, in general, we want to assume as little as possible. We want to try to make our equation, or whatever it is that we're working on, we want to make it as general as possible. And we don't want to make any assumptions as to anything like, so the idea here is, if we have a statement like two numbers, we're going to assume that they're different numbers. And since we're going to assume that they're different numbers, we're going to give them different names. And if it happens to work out in the end, like it did in this case, that they're the same number, oh, well, big deal. But we're not going to make that assumption going into it. Right?
Right.
Making sense? Okay. I just wanted to go over that before we get into what we're doing today, because some of the notation we're going to be using, it's real easy to get caught up with, and you'll see in a second, but we're going to refer back to this in a minute. Okay. So today we're going to be doing proofs involving integers. And so integers, if you remember, we've been denoting as the set big, this is called Blackboard Bold Z, Blackboard Bold Z, and it's the set of all of the counting numbers, right? 0, 1, 2, and so on, and all of their negatives, right? That is the set of integers, all positive and negative whole numbers, and 0. 0 is an integer, okay? And here are some facts. We're going to be, these two facts that I give you, we're going to be using extensively today, and we're just going to be using them as facts. We're also going to make a couple definitions here in a second, and we're going to be using those definitions extensively. And so here are two facts about integers. Fact 1. The sum of, and we'll do it like this, the sum or difference of any two integers is an integer. we're going to treat this as a fact. We could call this a theorem. And if I were to go and prove this, right? The theorem is a statement with proof. And I don't think I need to prove this. Do you believe this?
Yeah.
Is it right? You know, we could say, well, okay, let's be technical here. Any integer can be written in decimal form. And so you have 71.000. Any other integer can be written in decimal form as well. And it is also has a bunch of zeros. And so when you add or subtract any of those guys together, you're going to end up with zeros here and a whole number left over and blah, blah, blah. But we're not going to go into that. Like, this should be obvious. The sum or difference of any two integers is an integer. And so we're going to use that as a fact in our proofs. We're just going to take it as the ground truth.
Okay.
The second fact we're going to use is that the product of any two integers is an integer. Again, we could go through the rigmarole of proving this, but we're not going to. We're just going to take this as a fact, because do you believe that?
Yes.
Multiply any two integers together. How about -5 and 3? You get -15. -15 is one of those guys. Okay, there's no way out of it. Notice that it's not the product or quotient.
Mhm.
Right? That doesn't work, right? So we get sum or difference. That works. Product is, you can't undo product. We can't start dividing integers together and stay in integers. Sure, if you take 4 divided by 2, you happen to get an integer. But if you take 2 divided by 4, not necessarily. So these are two facts that we are going to be using all the time. They seem pretty self-evident, so I'm not calling them theorems. They're just facts. We can consider this as ground truth. Okay, so do you have this written down? And it would be good if you keep this somewhere in your sight for today as we're doing this. Like to have these either in your head, or it's really nice to be able to look down on your piece of paper and see them, especially when you put a bunch of stuff together and you're like, wait, I'm missing something here. Oh, that's right. Yeah, that's going to help me out. So, okay, we have these two facts. Now, what we're going to be working with integers today in particular are even and odd integers. We are going to be proving facts about even and odd integers. And for that, we are going to need definitions of even and odd integers.
Oh, yeah.
And so here's definitions. Definition 1. And I'm not even going to call it an even integer or an odd integer. I'm just going to say even number or odd number, because it's going to be easier for us. And I could do this instead of write out INTEGER. Like and the idea is, if you hear odd number, well, clearly we're talking about an integer. You can't have an odd fraction, right? 2.718 is not either even or odd. You have to be an integer to be either even or odd. Okay, so I'm just going to use the word number, but the definition is going to take care of this. So definition 1, an odd number is an integer that can be written in the form 2k plus 1. Okay, this is all one number here. This is all one number, 2k plus 1, where k is an integer. Okay. Now we're gonna go into this a little bit in depth. For right now, let's just get this on the page, and then we're gonna go just the way math is, right? They give you some kind of definition or some kind of theorem, and then go into breaking it apart. So we're just gonna get these up on the board and talk about this first. So an odd number is an integer that can be written in the form 2k plus 1, where k is another integer. Okay. Our second definition, an even number is an integer that can be written in the form 2n, where n is an integer. Remember what that means, right? That little e thing means is an element of, and so we're saying when I say n is an element of z, I mean that n is one of these things right here. It's one of those. It could be negative, it could be 0, it could be 1, it could be 700. It's just one of those things. Anytime that n is an integer. And now, just before we break into this, I just want to say, first off, there's nothing special about this being a k and this being an n. I could have written this both as n's. I could have written both of these as k's. But kind of like back to our original, the very first question I asked, right? When we're doing stuff like this, we don't want to say, like, if I said two numbers, I said x and y. I gave them different names because they may or may not be the same. And that's kind of what I'm doing right here. I don't want us to get it in our heads that these have to be in any way related to each other. And another thing is, if I were to say, okay, let's write down an odd integer, it doesn't matter if I use k or if I wrote this as an n, or, so what I'm saying is that if you're to write down just a general odd number, this doesn't need to be k. This could have been an n. It could have been an l. It could have been, and here's the thing, in general, when we're dealing with integers, when I said a number earlier, you said, well, x and y. And well, yeah, x and y are what we use for real numbers. When we're talking about integers, the variables that we usually use are I, j, k, l, m, and n. Those are usually the ones that we use. And so when you see something like that, you know generally that, yeah, we're talking about integers here. And the ones that we're most commonly going to use, and the ones we're going to be using today, are k, m, and n. But this is a convention. It doesn't have to be this way. I could have written this as 2x plus 1, where x is an integer. It's just that usually when we see x, y, and z, we're talking about real numbers. And so we're including decimals and irrational numbers and stuff like that. And so I'm just using this convention that's used throughout mathematics. And so when we're just talking about a general integer, we're using the letters usually k, m, and n first. And then if we need more, we'll bring in l, we'll bring in I, we'll bring in j. So you tracking?
Yeah.
Okay, cool. So let's break up let's get into these definitions here and see what exactly I'm talking about. First thing to notice, and I'm going to kind of extend this guy right here, is, well, all of the integers have this very predictable form, right? It just goes on like this forever and ever in both directions. And the thing to notice is, like I said, let's start with the evens. Every even integer can be written in this form. For instance, 2 is 2 times what?
1.
2 times 1 is 2. Is 1 an integer?
Yeah.
Yeah, so 2 can be written as 2 times an integer. 4 is equal to 2 times what?
2.
Okay, is 2 an integer?
Yeah.
Yeah, so this number 4 can be written in the form 2 times 2, and 2 is an integer. Therefore, 4 is an even number by definition.
By definition.
Also,
Okay.
going down in the opposite direction, -2 is equal to 2 times what?
-1.
-1. Is -1 an integer?
Yeah.
Yeah, so therefore, by definition, -2 is equal to 2 times an integer. So by definition, it is an even number. Now, ditto down here. What's -4? -4 is 2 times what?
-2.
-2. Okay. And we could go on and on. What about 0? Can 0 be written as 2 times something?
0.
2 times 0. Is 0 an integer?
Yeah.
Yeah. Therefore, by definition, 0 is even because 0 equals 2 times 0 and 0 is an integer. So it fits this definition right here. Now, when we do odds, I'm going to do odds in the different colors to kind of break this up. 3. Let's start with 3. 3, can we write that as 2 times something plus 1? 2 times what plus 1 equals 3?
2 times 1.
2 times 1. Okay, so now let's just see, does this fit the definition of an even number? Of an odd number. 3 is equal to 2 times 1 plus 1, and 1 is an integer. Therefore, 3 is odd by definition. What about 1? This is a tricky one. 2 times what plus 1 is equal to 1?
0.
2 times 0. Okay, let's move down. How could I get -1? 2 times what plus 1 equals -1?
Hold on, writing. Okay, 2 times -1.
-1, right? Now, here's the thing. If this were way more difficult and you started working on this for a couple minutes and you're like, wait, I'm not getting anywhere. What you could do, you could just say, wait a second, what am I trying to do? I'm trying to show that -1 is equal to 2k plus 1 for some number. And you could just say, okay, well, how about I just solve for whatever integer that is? And I could have said, well, okay, if I do that, I could subtract off 1 from both sides and I get -2 equals 2k. Then I could say, yeah, divide both sides by 2. And I get that k is equal to -1. Then I could just double check it. I'll plug it back into here and say 2 times -1 plus 1 is -2 plus 1 is -1. Yeah, okay, that's it. And so I got the right thing. So, but now we can really start to notice a pattern, right? Every time we move down 1, we're just like, we could skip odd numbers here. We could skip to the next odd number by just going 1 down. So this one's 1, plug in a 0, plug in a -1. If we plug in a -2, let's see what happens. -2 plus 1. Does that give me -3? Yeah. 2 times -2 is -4. Plus 1 is indeed equal to -3. And so -5 is what times 2 plus 1?
2 times -3 plus 1.
There you go, -3 plus 1. And what about 5? 2 times what plus 1 equals 5?
2 times 2.
2 times 2 plus 1. And so, okay, all we've done here, we've basically taken the integers, all of them, and we've broken them into 2 sets. And we're calling one of those sets odd, one of those sets even, right? So this is what I mean by this definition right here. It's that you give me, and this kind of goes both ways, right? Given any odd integer, I don't know, let's say 17. 17 is a good odd integer. I can write that in that form. And I could just say, okay, well, let's just make sure. 17, I believe, is odd. Therefore, it should have the form 2k plus 1. Does it? Well, I'm going to need to find what k is. And so how about we subtract 1 from both sides? Gives me 16 equals 2k. divide both sides by 2. And I get that 8 is equal to k. Okay, so then I'm just going to check it. Is it the case that 17 equals 2 times 8 plus 1? Is that true?
Yes.
Yeah. Is 8 an integer?
Yeah.
Therefore, 17 is odd by definition. Now, on the other hand, we could say, well, then this should, so it works in one way where you say you give me any odd integer and I could find a k that makes that, or I could find another integer k to plug in here to make that true. Another thing I could say is you give me any integer at all. I don't care if it's odd or if it's even. Let's do an odd one. How about 3? If I plug in a 3 here, what happens? I get 2 times 3 plus 1. What's 2 times 3?
6.
Plus 1 is
7.
okay. So again, and do you believe that I could have plugged in any number here and I would have ended up with an odd number?
Yeah.
Yeah, right. As long as what I'm plugging in is an integer, you should be fine. Even 0, right? Like, and that's, we saw that a second ago. You plug in a 0, that's an integer, and you get out 0 plus 1 is 1, and 1, yes, indeed, is an odd number. The same thing is true for the even numbers, right? Given any even number, how about 22? I could say, is that an even number? Well, is it equal to 2 times some integer? And you can say, yeah, if it's actually, divide both sides by 2, and you can see it's got to be 11. 11 is indeed an integer. Multiply it by 2, you get 22. Therefore, 22 is even by definition. Okay. It's the preliminary stuff that we're going to need to do what we're doing today. Any questions thus far?
No questions.
Okay. All right. So, proofs. Okay, so we believe that all integers can be grouped into even or odd, and we have a definition for that. Well, actually, let's talk about this first. So, with proofs, there are a lot of different kinds of proofs. What we're going to be dealing with today, and pretty much for always, is what's called a direct proof. And most direct proofs are of this form right here. If A, then B. And this could be any kind of statement, right? A could be any kind of statement, like if a number is positive, then it's greater than 0 or something like that, right? Like, or it could be a bunch of different things. It could be like in your homework, you had, well, I guess it was one statement, but you could have a lot of different things. It could be something like if, and we're going to say like 4 different things are true. Like if a number is positive and it has, and it is a rational number and it's Tuesday, then something else, right? Or maybe possibly multiple things, but this is the idea. It's that A could be a whole group of statements, a bunch of things, and then some other statement, which might be 1 or 2 things or whatever, but this is the general idea. Is that making sense what I'm saying?
Yeah.
Trying to keep this as general as possible for right now. And what we want to do with a direct proof is that we start here at A, right? We're going to say, we're starting here with all these assumptions. It might be multiple assumptions, right? It might be like you have an odd integer and a prime number, and then when you do blah, 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 you get something out of it. But what we want to do is start at A and end at B, kind of like going from point A to point B. And the way we get from A to B is by using facts, theorems, and facts. Oops, I already said facts. Facts, theorems, and definitions to get from point A to point B. This is very high level stuff, right? We're going to see examples of this to kind of to give us a better grip on how this all comes together. But this is the general idea, is that we're going to assume that that statement is true, whatever that statement is. Or maybe it's something like in my, with the first thing I said, the sum of two numbers is equal to 4 or something like that, right? Well, then we're starting with those numbers. So we're starting with whatever we're given at the beginning, and we want to end up with the final thing. The way to get there is to use this right here. Now, just as an aside, there are a bunch of other ways to do this. You could use logic to say, well, we could prove that if not B, then not A, and then do something where you could say, well, assume that A is false and then show that B is false or something like that. That's way beyond what we're trying to do right now. Right now, we're just going to worry about a direct proof where you assume the first thing is true and you show using facts, theorems, and definitions that that second part is true. The hard part in all of this is kind of transforming the given problem into this form right here, because it's oftentimes hard to see that it is indeed in this form, like trying to identify, okay, what have I been given and where am I trying to go? But if we think about it like that, if that's how we've kind of framed this in our heads, like when we're given a problem, which we're going to see in just a second, if we could identify, wait a second, what am I trying to prove? Where am I trying to end up? Then it makes it easier to see, okay, then all that other stuff is the stuff that I've been given.
Mhm.
So, okay, let's move on and do an actual example. So, and you'll notice that what I'm about to give you is not in that form at all. It's not if this, then that, but we're going to try to make sense out of that. Okay, so we want to prove, this is our problem. Prove that the sum of two, let's do that, two odd numbers is even. Okay, now let's break that apart. So where are we trying to end up? What do we want at the end? This is tough. This is tough. What should we see at the very end here?
Probably an even number.
An even, yes. We should at the end have an even number. We're gonna start with some stuff, but now we've kind of identified this, right? We've said, well, at the end, right? This is what I'm trying to prove, that something in the end is even. This is kind of like my B. So at the end here, when I'm doing all of this, I should have a bunch of stuff, some statement A, and do whatever it is, but in the end, I'm going to have B, which in the end should be an even number. What does an even number look like?
2n.
Yeah, there we go, right? Like by definition, an even number looks like 2n, where n is what?
Any integer.
Where n is an integer. So in the end, right, we should be able to, what it should look like, this is what's starting to form, right? Like in the end, I should have something like this. I should have something that says, okay, 2n, n is indeed an integer. And so I could say in the end, therefore, this thing, whatever it is even. And so it's starting to take place in my mind. This is the B. This is where I need to end up, right? And so now, what have I been given? What's my A? I'm kind of saying the sum of two odd integers. How could I write the sum of two odd integers?
Could you do like, because an odd integer is 2k plus 1, so wouldn't you just do that plus that again?
Well, remember in the very beginning when I said the sum of two numbers, and you said when the sum of two numbers, you told me to go x plus y. You gave them different names, right?
Oh, okay.
So how do we give two odd numbers different names?
Um,
The sum of two odd numbers. So, first off, just give me in general, just a odd number. What does it look like?
3.
Oh, no. A general odd number has the form.
Oh,
what?
sorry, 2k plus 1.
2k plus 1. Okay, so that's one of them. 2k plus 1. Give me another one. What might it look like?
2k plus 1.
Well, remember when we said so in one of them we used x, one of them we used y. If we're using k here, let's use something else over here.
2m.
There we go, 2m. And I like how you didn't say n, because we know that in the end, right, we've already used n, right? I guess in the way that we've done this. If you were just starting without having done any of this work right here, right, then yeah, I would probably use m and n, or k and n, or whatever. But the idea is, now that I've written this and I know that this is where I'm trying to go, I've already used n, and it's not necessarily gonna be the same as anything up here. In the same way, in our very first example, it's like, x plus y we said is equal to 4. We made those different. And if I said the sum of two numbers is equal to 3 times a number, well, we probably would have done something like this, 3 times a number, because we wouldn't assume that the x shows up over here, or that the y shows up over here, or that these are in any way related. So this is kind of the same thing we're doing here. It's like, you're telling me that the sum of two numbers, right, the sum of two odd numbers, well, they're not in any way related, the same way that x and y may or may not be in any way related. And so that's why we're giving them different names. But we could say the sum of two odd numbers, by definition, has the form. So notice, right, at the very beginning, I said we start with our statement A, use definitions, facts, and theorems in order to get to where we need to go. The very first thing I'm doing is saying, well, what's the definition of an odd number? I'm using that right at the very beginning. And this is very similar to the homework problem you had, right? Where it was like, show that if A is proportional to B, then B is proportional to A. And it's like, well, hold up. What does that mean? And so like the first thing we had to do is say, well, look, A proportional to B means this. And we used a definition. So that's the very first thing I'm doing right here. We're saying, so let's kind of step back for a second. We were given a problem. I'm trying to figure out what I'm given and where I'm going. And so we identified where I was going, because usually that's easier to say, okay, now that I know where I'm going, all the rest of the stuff is what I've been given. And so now I'm saying, okay, what the heck does this mean? The sum of two odd numbers? Well, I don't know. Odd numbers. What's the definition of an odd number? Well, by definition, an odd number has this form: 2k plus 1, where k is an integer. And another one, which I don't want to assume is the same one, has this form where m is an integer. You following me thus far?
Uh-huh.
It's making some sense, right? It's like you're just kind of at the beginning, we're just clawing in the dark. We're like, I don't really know. And honestly, when I first saw a question like this, it's like I have no clue how to even begin proving this statement. And somebody had to show me, and he did pretty much exactly what I'm doing right now, right? We have to, and this is the idea: is you're given a statement, we want to show that it's true. Well, let's break it into parts. Where do I have to go? What's the final statement that I should, it should look something like this, okay? But where do I begin? What am I given? Well, this is what we're given. How do we translate that into something that's useful? Well, we use a definition. By definition, the sum of two odd numbers, by definition, has this form. This is what it looks like. The only thing I haven't done here is say, okay, plus these guys together. Where do we go from here? Yikes. And this is where it gets ugly, but in the back of my mind, I'm thinking, well, in the end, I need to have 2 times 1 integer, right?
Mhm.
And so, well, I don't really know what to do with something like this. So I'm just gonna, I don't know, I guess group things that look the same. And this, honestly, I'm just like clawing in the dark here. I'm not too sure what to do. So I'm just going to rearrange this to group like terms together. I have a 2 times a variable, 2 times a variable. Let's just write those nearby each other. I have 2 times k plus 2 times m, and I'll just rearrange these ones like that. Okay, I have a couple constants. I know what 1 plus 1 is. What is 1 plus 1?
2.
2. Okay, so we're going to go okay. 2k plus 2m plus 2. Now, my whole goal here is to get this to be 2 times 1 number. And I notice that there's a 2 in every one of these terms. What can I do with something that's in every one of those terms?
Cancel.
You can only cancel if you have like an equation or something like that, which we don't really have. I mean, yes, I've written an equal sign here, but basically I started with just this right here. But if this were something like this, what would we do?
Factor it out.
You could factor it out. And it's like, and why would I ever come up with that? Well, because I'm thinking about my final goal here. The final thing I need to have is 2 times something. And so, and I noticed that, well, I can pull out a 2. And what I'll be left with is a 2 times a something. And what's left over? What's left when I factor out that 2?
K plus m plus 1.
Plus 1. Almost there. Is the only thing is that an integer? K plus m plus 1?
No. Yes.
What was one of the first things?
Oh, yes, it is an integer.
Because why
Because
is it an integer?
because well, hold on.
Okay.
The definition that we did for an odd integer is the 2k plus 1, and then where k is any integer, and then same goes for m, I think, right?
Well, hold on. So right now, we're almost there. All we need to do, if we say, well, this right here can be written like that, right? Basically, if you say k plus m plus 1, let that equal n, which is kind of what we're doing right here. And then we're where we need to be, just as long as n is indeed an integer. What was what was the first fact, not definition? What was the first fact I gave you?
The sum of any integer of any two integers is an integer.
There we go. And so now we have that. Now we could say, well, Since the sum of any two integers is an integer, then k plus m is an integer. And we know that 1 is an integer. And so the sum of an integer plus an integer is an integer. Therefore, n is an integer, because we use those facts right there. Well, notice how messy this is. And this is something I didn't really talk about at first, but we're going to talk about right when we finish this. But now let's just see. We took the sum of two odd integers and showed that it could be written like this, where that is an integer. Therefore, it is even by definition. That's where we wanted to end up, right? You believe that? Did that make sense? Did you follow that?
Yes.
Okay. And now here's the thing. This is really messy, and I would not accept this as a proof. This, and I'm going to say, just for now, until you get really good at this, which is going to be years and years until you get good at this. What I would suggest you do, whenever you're doing any proof, is all of this right here, all of this crap that we have done, I call this scratch work. And on my page, on my paper, when I'm doing a proof, right, I have my statement, right, which says prove such and such. What I do is I put a big line down the middle. And on the left-hand side, I write scratch. On the right-hand side, I write proof. And all of this that we've written right here would go on the scratch side, because like I said at the beginning, I wasn't sure where to go. I just started playing around with stuff until I noticed, oh, hey, look at that. This is where I am. This is where I need to go. And I'm almost there. I can see if I pull out a 2, then I will be in that form right there. And now I could say, yeah, that thing is indeed an integer. Therefore, we could write it as to n. And oh, there we are. That's where we wanted to end up. And so this is what my scratch looks like right here. But when I go to write this up as an actual proof, I'm going to kind of formalize all of this and make it look really nice. When you first start off doing this, it's better to be a little bit more verbose, right? Like, yeah, you could just do this. Like, if you just wrote that, you would technically be correct. But this isn't about communicating, or this isn't about getting the right answer. This is about doing exercise for your brain, right? And what we want to do is, after having done this work, we're going to go back and really nail down why all of these statements are true. And we're going to as though we're communicating to somebody else, because that's what this is, as though we're communicating to another person, hey, I'm trying to show you that this is true. Let me explain. And I'm going to use words. I'm not just going to write down a bunch of crap like this, because that doesn't mean anything. Like, so this is what this would look like to me. This is how I would do something like this. I've started here, I pulled all this stuff apart, and now I have an idea for how my argument is going to shape up. And I'm going to say, okay. And it's nice to start off with something like given, like you're given 2 odd numbers, right? That's what they say. So given 2 odd numbers. Well, they have the form . 2k plus 1, and what do we use? 2m plus 1, where K and M are integers. And we could make that like that right there. We don't have to do K is in Z and M is in Z. This is just a lazy way of saying that both of them are in integers. Okay, so all I've done at the beginning, right? That's what we said. We're like, well, let's just use the definition of integers like that. And now I'm explaining to somebody, right? And that's what I'm doing right here. Given two odd integers, right? Starting with part A right here, given two odd numbers, they have the form this and this. And now, well, now we know what we're talking about here, right? We're talking about the sum. So it's all right to go ahead and jump to. And we're going to say, so the sum 2k plus 1 plus 2m plus 1 is equal to, and now we're just going to go through and do this stuff, right? 2k plus 1 plus 2m plus 1 is the same thing as 2k plus 2m plus, and we could go ahead and skip a little bit. I mean, this is pretty explicit what we're doing right here. And now here's the bread and butter, right? We pull out that 2. And right now, all I've done is I've just kind of gone back over my scratch work and I'm seeing, okay, this is my scratch work. I know this is where I need to end up. And as I'm writing this down, I'm like, is this clear? Do I need to explain what I'm doing here? No, I don't need to say every little thing like I'm dropping the parentheses. I'm rearranging the equation. I'm factoring out. Like we're all at the same level of math here, right? But now when we're explaining why these things are justified, we're going to need to use our brain. We're gonna need to write some stuff down. Okay, so we said, okay, that's the sum of two odd numbers. It can be written as that. And I'm going to say now, since k plus, well, how about since k and m are integers, right? Which we said right up here. I'm looking back to say, did I ever say that? Yeah, I did. I did say that that was true by definition. Okay, since k and m are integers, then k plus m is an integer, and k plus, and we could go ahead and skip this, but you see what I'm saying, right? Like, it's not just that we're writing this crap out. We're going back over this and putting this into our heads to make sure that we are even following our own logic here. And going back and doing this will really help get this, well, it'll make your exercise better, right? But I'm going to say, yeah, since those are integers, then k plus m, and I could be really verbose here, and I'm just going to go ahead and be really verbose because we're just starting this stuff. Because reasoning. K plus m, since they're each integers, then k plus m is an integer. And so is k plus m plus 1. Now, we could go ahead, we're technically done right now. We could say, therefore, this has the form of an integer by definition, but since we're just starting this, let's be even more explicit, right? Let's try to every single step along the way. Let's really draw it out as though you're explaining to a classmate who is just struggling, right? You imagine, anytime you're writing a proof, imagine you have a classmate that you're trying to explain all this stuff to, and they have no idea what's going on. And so you are trying to say, okay, look, I really want to walk you through this. So it's not just that k plus m is an integer, because they're both integers. 1 is also an integer. So you add these integers together, you get an integer, right? Remember, Justin said that. He said that the sum of any two integers is an integer. And so then you add that to 1, it's also an integer, and your classmate's like, yeah, okay, I'm kind of following. So you say, okay, well, maybe you don't see this. You don't see it yet? Okay. Then since k plus m plus 1 is an integer, then, well, we could rewrite that. K plus m plus 1, we could say, well, that's n, where n is an integer. And they're like, oh yeah, okay, I follow you. Therefore, right, and now we're going back to definitions. Therefore, and now, and in the last step, I'm going to put this all together. I'm going to say, therefore, this plus this equals, so 2k plus 1 plus 2n plus 1 equals, what did we just say? 2n, where n is an integer. And thus, the sum, referring back to the original sum that we're talking about, the sum is even by definition, which is what we wanted to prove. And you put a little box like that. That little box right there, little cube or square, a little filled in square, it means QED. You know what QED is, right?
Yeah.
Right? Quod erat demonstrandum, that which was to be demonstrated. Or like I said at the beginning, this is true. There it is. That is your proof right there. When you start doing proofs, it's better to err on the side of thinking about explaining this to the worst person in your class, right? Like, imagine somebody who is not even close to following along, and you want to really explain to them why something is true. And so, yeah, this may seem pedantic. It may seem like, man, you don't need to say all that. Really, Justin, all you needed to do is this. And it's like, yeah, but we're trying to exercise our brains here. Like, yes, you're right by writing this. This is correct. But we want to go a little bit above and beyond because we're doing this for ourselves. This is our exercise, right? This is part of this. And can you see why this is a good fit? Like, why really writing it out like this is actually good for your brain?
Yeah.
Yeah, I mean, it's a little bit extra work. I'm sorry, buddy. I'm sorry, I'm busy. So, okay. Does all of this make sense?
Yeah, I'm familiar with proofs just because I did Euclid last year,
Okay.
and like this is literally all we did. We didn't write it all out like that. We just put like, so we would write out, you know, the proposition or whatever.
Right.
F,
Right.
And then we on the side we would put like definition 1 or definition 2.
Mhm. It's very, very similar. And what I want, what is really, really good is to, instead of like, and yeah, I kind of do the same thing where I'm splitting stuff up, right? But again, this is, don't even think about it like that. Like, we're not doing like, here's my work, and then over here, I'm going to explain what's going on over here. In fact, what I would much rather have is you just do this on your own, right? On a separate sheet of scratch paper, and then you put it all together like this, right? And this is what you turn in right there, right? And the idea is that we're just talking. This is like a conversation, right? And it's not like, here's my math, and here's the reason why I could do my math. Here's my math, here's the reason why I could do my math. That's not how we communicate, right? We don't communicate that way. We communicate in language. And this is, yeah, there's some math in here, and there's some steps that we're not justifying. But all of the big steps, right? They are being justified, and they're done in a conversational way, right? So, but again, in some cases, yeah, you will do something like this, and you'll say, you know, by the associative property or whatever it happens to be, if, you know, that's the idea. In this case, we're not really worried about this type of stuff. We know that we could drop parentheses. We know that we could rearrange equations. Like, that's stuff we don't really need to say. But when it comes to the bread and butter of this stuff, the definitions, why it's the case that k plus m plus 1 is indeed an integer, we need to say why, right? Or at least say, like, we know this is a fact. I'm referring back to this fact. We don't need to say by fact 1. It's just like, but we do need to say, like this is true. This is why that this all works. So
Right.
okay, let's do another another with integers here, because there's a kind of a yoga to it, right? Yeah, do you have all this?
Yeah.
Erase this? Okay. So let's do this. Prove that the product of two odd numbers is odd. Okay, where do I want to end up? What should I end up with?
An odd number.
Odd number. What does an odd number look like?
2k plus 1.
2k plus 1. So I should have in the end 2k plus 1, where k is some integer. You can't forget that, right? Like that, in order to be able to say, then by definition, part of that definition is that that k needs to be an integer. So we're going to have to show that in order for in order to use the definition in the first place. So I'm telling you, write this down. Don't just have this in your head. Have this written down, because this will, trust me, it'll make the world of difference to have it somewhere on your page. Something happens when you write something, you watch yourself write something, and as you're reasoning along and doing all your scratch work, you see it again. Something happens in your brain that really helps keep you focused. And it's so easy to go off the rails when you start, writing proofs. So I highly recommend you have this. Another thing, we did it, and I meant to say something about it before I erased it. At the very end, you'll notice I said, therefore, the sum, and understanding it was the sum of two odd integers, is even, right? I basically restated the same thing at the beginning. And that's a good habit to get into. And you don't really see it, like, I mean, if you're reading like a research paper in mathematics or something like that, they don't bother with that. But when you're first learning proofs, it's really good to actually write it out. Again, for the same reasons, like you're reinforcing it into your mind. And if you've screwed up and you go to write at the end, like, therefore the sum of this is even. Wait, I didn't actually prove that. It's like, it's a nice check for yourself. So I highly recommend that at the end of all of your proofs, you kind of restate the original question, and you're summing up the whole conversation. You're saying, therefore, but in this case, it'll be, therefore, the product of two odds is odd. And so we're going to do that. But so this is where we need to end up. We're going to need to have something that's 2k plus 1. Okay. What am I starting off with? The product of two odds. So what do I need to write?
Okay. So 2k plus 1 or I guess no, since we're winding up with 2k, I thought we were going to go through. Sorry. So 2m plus 1 divided by 2n plus 1, I guess.
Did you say divide by?
Yeah, I misspoke.
Product.
Right.
Okay. So we're going to multiply, right?
Yeah.
Okay. So 2m plus 1, and then what?
Times 2 n plus 1.
N looks good. N looks good. And now here's the thing, right? It would be really good to use parentheses here.
Right.
So let's go ahead and do that. I'm going to say, okay, that's my odd number. Maybe it's 3. And this is an odd number. Maybe it's 5. Another thing that I didn't really talk about this, but I would actually just check this before even starting, right? And say, wait, is that true? Because I don't want to try to prove something that's not true. So let me just get two odd numbers. Let's just take 5 times 3. Okay, 5 times 3 is 15. 15 is odd. Okay, this sounds like it could be true. If I ended up with an even number, I'd be like, wait a second, I don't want to try to prove something that I've just shown isn't true. But the thing is, I never want to use a special case in my proof. I never want to say, well, like the worst thing you could do is if I say prove that the product of two odd numbers is odd, and you go, well, 3 times 5 is odd. They're both odd, and the answer is odd. So there's your proof. Like, you've shown for one case. How many integers are there, Kayla?
Oh, a lot.
Infinitely many, right? So if you wanted to do this type of thing, you would have to, for the rest of your life and eternity, for the entire afterlife, sit there and just go pairs of integers and prove, yep, they're odd. This one's odd. Yep, this one's odd. This one's odd. This will never work. But if we use, and this is the great thing about having these stupid abstract definitions, is we could say, we know for a fact, we've already shown this, that every odd integer looks like this. And you give me any two odd integers, maybe they're the same, right? Remember with x plus y, maybe in the end it ended up being the same, but it didn't matter. We're going to assume they're different at the beginning, and if they happen to be the same, it won't matter. And so that's what we're doing right here, saying give me any two odd integers, any of them. And we're going to show that when we go and do the blah, 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 blah. So, okay, that times that. What do you want to do? That's the only thing we really can do in this case. How do
we FOIL it?
That's pretty much the only thing we can do. Yep, we're going to FOIL this guy. So, first gives me what?
2m times 2n is 4mn.
Okay. 4mn. Okay, outer gives me what?
2m.
Okay, so plus 2m. Inner gives me what?
2n.
2n. Okay, and last gives me what?
1.
Plus 1. Okay, now I'm going to kind of stop and say, okay, it looks like I am a little bit closer here. Because what I need to do, in the end, I need to have something that has a plus 1 on it. Hey, that has a plus 1 on it. That's cool. If I could just get the rest of that stuff to look like 2 times something, then I'll be, in fact, I'll be there. Is there a way I could get the rest of this stuff to have 1, 2 out front?
You could factor it, right?
Yeah, exactly. And that's kind of what's going through my head. What's really nice, like I suggested, I had it written down here so I could see, like I'm looking and saying, well, hold up, man, that is really close to that right there. And because we have the plus 1 hanging out, that's cool. All I need to do is get a 2 out there. And if I were to, can I do that? What would be left over on the inside?
You have 2mn.
Yes.
Plus m plus n.
Plus m plus n. And now, are we there? Is that an integer?
Yes.
Yes, and we know that because, right, we knew that m and n were integers to begin with. We didn't write it down in our scratch work because we're lazy, but we know that they're integers, so that's an integer. And the product of any integers is an integer. And so 2 times m is an integer. Multiply again by n, still an integer. Add that to an integer, still an integer. Add that to another integer, still an integer. And so we could say, yeah, that's how my proof is going to look. I'm going to have to say, remember, this is an integer. This is an integer, so that's going to show up over here. And then we could say, yeah. In fact, why don't we give it a name? We'll call it k, 2k plus 1, where k is an integer. Yep, and that is indeed where we wanted to end up. Okay, so here's my proof. Given what?
Oh, your video just went out.
Uh-oh. All right. Last time this happened, I had a really easy fix, and let's see if this fixes it. Ho, ho, ho. Nice. All right. So we're starting off. Where are we starting off? Given what? What are we
Given 2 odd numbers, I guess.
2 odds? We can write as, I'm just looking over here. Okay. 2m plus 1, 2n plus 1. And 2n plus 1. Where? What about those guys?
Hold on. 2 plus 1 and 2n plus 1. They're integers.
Right. And here I'm using the definition, right?
Right.
That's, that's most proofs start out that way. You're given something and you're like, what? Well, I don't know. Let's just write down the definition and we'll see. By definition, it looks like this. Okay. So then the product of the two is, and we'll just write it out. It's that times that. Okay. And we've already done this work, so we're just going to go ahead and jump to the chase. We'll say that is 4mn plus 2m plus 2n plus 1, which equals 2 times 2mn plus m plus n plus 1. And we could say, okay, now this was like the bread and butter right here, right? We need to, in order to put this to work in our definition, we need to tell our classmate, like, hey, check it out, dude, that's an integer. That's an integer right there. And so we're already in the form of one. So let's be explicit about that. We could say, I'm sorry, buddy. Since m and n are integers, then, and we can be really explicit, then we could just say, then so is 2mn. And if you just write that, I'll know that you're referencing that fact, right? Like, because the product of integers is an integer, okay, so is 2mn. And therefore, so is 2mn plus m plus n. Now our classmate's really slow. They're still not quite picking up. They're like, but that doesn't look like that right there. So we're like, okay, let me just really, really drive the point home. We could say, therefore, 2mn plus m plus n equals k for some, we don't know which one it is, it's for some integer k. Or in fact, I'm not even going to write it like that. I'm just going to say for some k in z, because integer takes a minute to write out. For some k in z. Therefore, or thus. You end up using since, therefore, and thus like all the time. And yeah. And so, okay, therefore, right? Now, what do we have? We could say, therefore, 2m plus 1 times 2n plus 1. Here, I'm going back to the very original thing, right? 2n plus 1 is equal to 2k plus 1. See, that was equal to that. Finally, putting it all together. And k is an integer, so the product is odd by definition. Definition of odd number, but there you go. That's what we wanted to prove. QED. And that is what we're doing. Always assume that the person, when you first start writing proofs, always assume that your audience has a very low level of understanding and that you need to explain every single little step. Of course, you don't want to get too pedantic about it, like, well, we know that we could FOIL this out. That's not really the point. You know, we're at the point where we could get that. It's these connections, right? And though, again, the whole reason that we're doing this and taking these painstaking things isn't because the rest of your life your proofs are going to look like this. It's to get your brain into this swing of things, that we're following one step from another. We're never just going to say, oh, this equals that and that equals that. We're going to explain why things are equal to each other because it's good for our brains. So, okay, we're running over, but I do want to do one more time how a really good proof would look with one of your homework questions.
Okay.
So, okay, this was, okay, so you got all this?
Yeah.
Okay. So one of the things, it was, let me just look it up real quick. Sorry, I should have had this ready to go. I meant to, and then I forgot. Okay, so one of the questions. Is it always, sometimes, or never true that if A varies inversely as B, then B varies inversely as A? And, oh, I hate how they wrote this. And 1 over A varies directly as, there are two different proofs there. And so we're going to just look at the first one. So is it sometimes, always, or never true that, and they even give it in an if then, which is great. If A varies inversely as B, if A varies inversely as, I think a minute ago I said proportional to. Sorry, that's another way of saying the similar thing. Inversely proportional to, or something is proportional to. So if A varies inversely as B, then B varies inversely as A. Is inversely as A. So we're not quite sure, but I'm going to assume it's true, and we're going to see if on the other hand we find that it's not true, then we'll say no, and we'll have already done the work, and then our proof will look a little bit different, but we will have done the work. So I'm just going to assume it's true, and we'll see if indeed we can connect these dots. So what is my ending statement? What am I trying to prove?
Oh my goodness. Okay.
Yeah, this is tough. But remember, at the very beginning, we had an if-then statement. We had if stuff, then other stuff. And so the other stuff is what we're trying to prove in this case.
Right. B equals,
Oh yeah, you're getting ahead of me. I'm just talking about this statement right here.
okay, so
what we need to end up with is this right here. That statement is where, that should be our final thing. If this is all true, we should be able to say, therefore, B varies inversely as A. So I'm really, like,
okay.
at this first step, I'm not thinking too hard about, wait, what does that mean? No, we're just trying to identify this statement. What's my beginning? What's my, or rather, what am I given and where am I trying to go? So where I'm trying to go is at the very end, I should be able to say before B varies inversely as A.
Right.
And what am I given? Where am I starting?
A varies inversely with B.
Yeah, so we're going to say in the beginning, we should say something like, suppose that A varies inversely as B. Now, I like to personally have an idea of where I'm trying to go. And when I read this, that doesn't give me an idea of where I'm trying to go. So let's use the definition of variation to peel this apart. What does this mean? Inverse variation. If B varies inversely as A means what?
B equals K over A.
There we go. It means that B equals K over A. And now notice how similar this is for some K that's non-zero. Like when we were doing this with integers, it turned out that K was an integer, right? We had to say that every time, like K has to be an integer for this to be true. Well, in this case, K has to not be zero.
Right.
So for some K, that's not even zero. And so that's what we're going to need to show. Because if we're doing all this work and then we end up with K actually equaling zero, then we'd know, hold up, that has to not be zero. Otherwise, it doesn't fit this definition. And so whenever we're using definitions and proofs, we need to be painstaking that we have all the little bits, right? And so in this case, this is where we need to end up. We need to show that this is true. Okay, so I have my goal. I know where I'm trying to get. Now, suppose that A varies inversely as B. What does that mean?
A equals K over B.
Suppose that A, so suppose that A equals, suppose that A is inversely proportional to B. That means that A equals K over B. What about K?
K is a integer that can't equal zero, right?
Not an integer. Not an integer in this case. We were working with integers earlier.
Right.
We said that, the integers we write as K and stuff like this. This is now we are completely out of the realm of integers. We're talking, this could be any real number as long as it's not equal to zero.
Okay.
So yeah, this is when in the book we used K, right? It would be nicer if they used C for a constant. And that's what you usually, well, K or C for constants, but K is often used as an integer, which is confusing. But so where K, and we'll say for some K, for K not equal to zero. Okay. So by definition, if A varies inversely as B, if that's true, then there is some K that makes this true. Now, how do I turn this into that right there?
Oh boy.
So you have an equation involving denominators. What do we want to do?
Kill the denominator.
Denominators, how do we do that?
Multiply each side by B.
There we go. So I'm going to multiply this side by B, and I'm going to multiply this side by B. And what happens?
Hey, you cancel the B.
Cancel that B, and I'm left with BA equals K.
And then you divide by A.
Aha, and it's so nice to have that written right there because like without all this written down, you can look at that all day and go, what the hell am I trying to do? Right. But here it's like, oh, hey, look at that. I'm almost there. In fact, all I need to do, just like you said, I'll divide by A, divide both sides by A. Okay, now I have B equals K over A. Is K equal to zero?
No.
No, we even said it right there. K is not equal to zero, and K is not equal to zero. So that's what we want to show. That is by definition, then that thing is, then B varies inversely as A by definition. So when I'm going to put all this together, I'm going to start off by saying, well, if this, then that, if the first thing is true. So suppose the first thing is true. Proofs often start off with the word suppose or the word given. In this case, like, because we were given two integers in the last case, right? In this case, they're giving you a proposition. And so you usually say, suppose that this proposition is true. So we're going to suppose that A indeed varies inversely as B. So then we're going to say, by definition, because that's how we got from there to there. We said, wait, what the hell does that mean? Oh, right, that's what it means. We translated it out of human speak into an equation. And so we used a definition to do that. So I'm going to say, by definition, there is a K. And this is how I said it the other day. This is how I kept saying it Friday. By definition, there is a K not equal to 0 such that that one, we already got it. A equals K over B. So we're just going to go ahead and copy a couple of these guys down. In fact, since we've already done the work, I could be pretty confident that I could just say, okay, multiply both sides by B gives me this right here. Divide both sides gives me B equals K over A. And we could say, now finally, right, we had to make sure that this fit the definition. And so it fits the definition. Let's tell our slow classmate, just like, hey, notice, look at this, like, oh, since K is not equal to 0, since K is not equal to 0, then B is inversely proportional to A by definition. By definition. Which is what we wanted to show. Which is what we wanted to show. Right there. I didn't go ahead and, since this one's kind of short, right, I didn't go and restate the entire thing. But as these get crazier and longer, you go back and read your proof. And imagine that somebody just told all these things to you. And if at the very end, you're like, what were we trying to do again? Then just restate the whole thing all over again and to kind of refresh the brain, because it's good for your brain too, because you get lost. If you're lost reading your own proof, you just got, you need to revisit, right? But in this case, this one's so short and so sweet that it's like, I'm tracking. We don't really need to go in there. That was what we wanted to show.
Okay.
And, there we go. Now, I would like for you to redo 31 and the second part of this one. But one thing to notice is that, actually, give me just a second. Let me look at something. Yeah, okay. We kind of talked about this on Friday, is that the K may not be the same K in the end, right? It's just that it's a constant, right? So if you're rearranging stuff, I'm not 100% sure if you're gonna have to in this one. You might know, yeah, with 31, you're probably going to have to rearrange a constant. And don't take my word on that. I'm just kind of looking at this, and then I have like 20, or at the end of class, my brain is about as dead as your brain. So the thing is here, I think we did that. It's the whole point is that we are not. Let's say that we had something like this. No, we're doing our work now. Can I erase all this stuff?
Yeah.
Okay. So now let's just do it. Well, we'll just do it. So we want to prove this. If A varies directly as B, then B varies directly as A. We want to prove or disprove this. And so we're going to say, all right, let's do some work here and see. So we do the same, we use the same kind of reasoning. We identify where we're trying to go. Our final statement should look like this. It should look like B varies directly as A. And everything else is what we're starting with. And so we're going to suppose that this part is true. And we'll say, okay, that's where we're going to end up. That's where we're going to start. But then where we want to end up is, well, I want to actually see what that looks like. So what does B varies directly as A mean?
B equals KA.
For some what now? I have to say something particular about K.
Constant.
Constant, and it's in particular not equal to what?
0.
For some constant K not equal to 0. Otherwise, it does not fit the definition. So we're going to have to show that that's the case. Okay. Now, here's the thing about this. And we did this last time and we actually got away with it. And remember, when we were doing stuff with integers, right? In the end, like if we wrote 2k plus 1, and you said, okay, well, an odd integer is 2k plus 1, and I was like, no, we don't know if it's the same one or not. And then this last time, I didn't make a big fuss about it. That's because I knew where that problem was going, and it just happened to be the case that it worked out for both of them. But in this case, it might not. In fact, it's not going to. And this is why I'm taking even extra time, and we're way over now, but because this is important. And to be, I probably should have used different letters at the very beginning. But in this case, we are going to make sure. So you remember, right, when we had like 2k plus 1 at the bottom with one of our integer proofs, and we said, well, give me two numbers. We wanted to use different numbers, and you could see why, right? We wanted to give them different names. So let's use a different name here for the beginning. We're going to say, okay, suppose the beginning. Suppose that A varies directly as B. Then by definition, what is true? What does that mean?
A equals KB.
A equals what, B?
Oh, right.
Ah, exactly, right? Trying to keep this as general as possible, and we're thinking about our very first question. Two numbers. Well, we used x plus y. Why? Well, because we don't know if they're the same or not. We can't assume that they're the same. They might be the same. And in that last case we did with inverse proportionality or inverse variation, then yeah, they happen to be the same one. But in this case, we don't know that for certain. So let's give it another name. What name do you want to give it?
W.
W. A equals W. B, where, what about W?
W cannot equal 0.
W cannot equal 0. Okay. Now, we need to get from here to there. And we're almost there, right? Like, I mean, we could say, well, let me just to really be certain right there. We can even go like that to make that one look even more like that. But boy, it would be nice if we had that B all by itself. How do we get that B all by itself?
You divide both sides by W.
Divide both sides by W, and we do that. And we get, let's see, how about B equals, but now I could kind of see where I'm going here. I need to have some constant in front of A. So why don't I rewrite that as how about 1 over W times A?
Hmm.
Now, remember when we were doing our stuff with integers and at the end we ended up with something like this, 2mn plus n plus m. And then we said, man, that almost looks like the very last thing. Like we're just noting that that is an integer and then we gave it a new name. Let's do the same thing here because this almost looks like this right there.
Mhm.
Say, well, here's the thing. There's only one number that we can't divide by, right?
0.
And it just so happens that this is the one number that this thing could never be. And so we could say, well, since since W is non-zero, then 1 over W is equal to, well, why don't we bring in that nice little variable right there, is equal to some constant, and that constant cannot be zero. Because
Right.
there's no way to divide by something that's not zero and get zero. You can only multiply something by zero to get zero. So that's impossible, right? But here I'm telling my rather slow classmate, like, hey, look, like this has to be true. Like when you do this after dividing here, because that guy was not zero, then you ended up with a brand new constant. Let's give it a new name because it's going to make this look nice. So we're going to give it a new name, and it happens to be the fact that, oh yeah, and it's nice that I wrote that right there because I was looking for that the whole time. Like it had to be the case. So k is not equal to 0. And now we're done. That is what we're looking for. So then B is equal to K, because we're doing that substitution, times A, and K is not equal to 0, thus true by definition, etc., etc. What I would like for you to do for homework is to, this is problem 31. I would like for you, now remember, this is the scratch. This does not look nice. I would like to see your full proof, your full write-up for that guy.
Okay.
Also for homework, do 32, both of them. There's two separate ones. We just did the first part.
Okay.
The second part, so I'll be really explicit about this. Right? For 32, there are two problems I want you to do. We're going to call it 32A is going to be. So for 32, prove A is exactly what we did in class, but I would like to see your writing. And it is if A varies inversely as B, then B varies inversely as A. B varies inversely as A. I want to see you write up. I know we just did it, but I'd love to see you write it up. B. The second part is if A varies inversely as B, then 1 over A varies directly as B. So you've seen A. We've done it in painstaking detail. B is going to be very similar. I mean, it's very similar, right? Like the mechanics of it, right? You're going to have your final thing, and you're going to translate what the final thing looks like. Start with your beginning thing and see how you could get those guys to come together. Then once you've done your scratch work, write it up like you're explaining it to a very slow classmate who's really struggling. Number 31, same deal, and I pretty much did it. We're going to prove that if P varies directly as Q, prove the statement. If P varies directly as Q, then Q varies directly as Q varies directly as P. And that was what we just did right here. But of course, I didn't write it up and make it look nice. Notice that in all of this, I never used any cases. I never said, well, let's look at 5. Let's look at 7. Let's see what happens when we throw a 2 in there. Like,
Right.
that's great stuff to do. Oh, I'm going out. It's going out. Is it going out? I
You're
froze.
frozen.
Oh, you know why? I'm getting a call from spam. Okay, so, and that is great to do when you're trying to get a handle on it. Like in your scratch work, you know, like I said before we started the odd problem, it's like, well, let's just take 2 odd numbers and multiply them and just see if this even makes sense. But that never shows up in our proof because, again, that's a case. In one case, it might be true in one case, but it could be false in many other cases. But I only did that just to kind of give myself a feel for, yeah, okay, this sounds right. So, but when we're doing proofs, we want to keep it as general as possible every single time. So, okay, finally, your homework is to do these with these special instructions and one more proof. Prove the following statement. Which one did I want you to do? Let's have you do that one. The product of an even and an odd, an even number and an odd number. The product of an even number and an odd number is an even number.